If you blindly grab an open source model today, and just push it straight into your production backend.
Oh, you are going to hit a wall.
Right. You're going to hit one of two massive walls incredibly fast. Like, either your cloud compute bill is going to look like a phone number by Friday.
Which is terrifying for any engineering team.
Totally terrifying. Or you're going to accidentally breach a tech giant's bespoke commercial license, right? And just invite a total legal nightmare.
Yeah, the cease and desist email is not a fun one to open.
Definitely not. So welcome to the reality of the current AI ecosystem. Today, we're taking notes from the LLM Mastery podcast and really just pulling them apart. We want to figure out how to actually engineer around these roadblocks.
Because it's not just theory anymore, right?
Exactly. The goal here is simple. We want to cut through the theoretical hype and give you, the developer tuning in, a concrete strategy. We're talking navigating, selecting, optimizing, and legally deploying these open source models into real-world applications.
It is exactly the conversation we need to be having right now. I mean, the landscape has fundamentally shifted. It's no longer about, can we build this?
Right. It's how do we run this without bankrupting the entire department?
Exactly. We are way past the phase where just slapping a basic API wrapper over a cloud service passes for a scalable product architecture.
Yeah, that doesn't fly anymore.
No, it really doesn't. If you want true control, low latency, and actually sustainable margins, you have to get your hands dirty with the open source side of things.
So let's start right at the epicenter of that open source side. If you're building a modern AI pipeline, it feels like all roads essentially lead back to Hugging Face.
Pretty much, yeah.
But okay, let me push back on this right out of the gate, because we already have GitHub for code discovery. We've had it forever.
Right.
So why did the industry need an entirely separate hub just to host machine learning projects? I mean, it kind of feels like we just reinvented the repository.
That is a very common reaction, honestly. But it totally misunderstands what an AI model actually is in practice.
How so?
Well, think about it. GitHub is brilliant for managing logic, right? Your standard source code.
Sure.
But an AI model isn't just logic. It's a massive combination of code, very specific deployment environments, and immense weight files. I'm talking gigabytes of raw tensor data.
Oh, right. The actual weights.
Exactly. If you go back just a few years, trying to deploy a model off a raw GitHub repo was a total nightmare. You would spend days, literally days, fighting CUDA out-of-memory errors.
Oh, man, don't remind me.
Right. Or resolving obscure Python dependency conflicts, or just trying to reverse engineer whatever custom PyTorch wrapper the researchers threw together.
It was basically dependency hell.
Total hell. So Hugging Face didn't just provide a host for the big files. They built a standardized interface.
You're talking about the Transformers library.
Yes. The Transformers library abstracts away all that fragmented garbage. Whether the model was trained by Meta, Google, or just some independent researcher in a basement, Hugging Face wraps it in a unified API.
So it's basically plug and play.
Exactly. You literally just use AutoModel for causal LM dot from pre-trained, and it handles the tensor loading, the device placement, the architecture mapping, all under the hood.
That is so clean.
It really is.
Yeah.
And you pair that with their Datasets library, which standardizes the heavy I/O bottlenecks of feeding data into these models.
Which is always a huge pain point.
Huge. But with these tools, suddenly the friction of the discovery phase just drops to near zero.
It's like, I like to think of Hugging Face as this massive, bustling digital mega warehouse, right?
That's a great analogy.
That you walk in, and instead of digging through unmarked boxes, the aisles, like transformers, data sets, spaces, they're all perfectly labeled so devs don't get lost.
Yeah, and speaking of spaces, that's another game changer. It's essentially just a managed environment for Gradio or Streamlit apps.
Right, so you aren't even writing local testing scripts anymore.
Exactly. You find a model, you click over to Spaces, and you can immediately test its inference capabilities in a visual UI before you ever even run pip install.
Wow, so you can validate if a model is actually good in like 30 seconds.
30 seconds rather than 30 hours, yeah. But, dropping the barrier to entry that low creates a completely different kind of problem.
The noise.
Yeah. Hugging Face currently hosts over 500,000 models.
Which brings us to arguably the most paralyzing part of the process for a dev. You're staring at a search query with 500,000 results.
It's overwhelming.
Massively. So let's talk about the selection framework. Based on the notes, the current heavy hitters are Llama from Meta, Mistral from Europe, Quinn from Alibaba, Phi from Microsoft, and Gemma from Google.
The big five, basically.
Right. But if I'm an engineer and I'm tasked with picking one for a new microservice, my immediate instinct is to just pull up the MMLU or human evil benchmark leaderboard.
Well, please don't do that.
Well, why not? Like, I just find the one with the highest score that fits my memory budget, right? And I deploy it.
And that instinct is exactly how you end up with a maintenance disaster at 3 in the morning.
Wait, really? Just going off the best benchmark?
Yes. Raw benchmarks are only one pillar of a 4-part framework you need to be using. You have to look at capability, size, license, and community support.
Okay, 4 pillars.
Right. And I would argue that for a real production environment, community support is vastly more important than like a slight edge on a theoretical reasoning benchmark.
Let me stop you there, because that sounds counterintuitive. Why would community support outweigh raw reasoning capability? Like, if the model writes better code or extracts JSON more accurately, isn't that the entire point of using it?
In a vacuum, sure. But software engineering does not happen in a vacuum, you know? Let's say you pick a highly obscure independent model just because it scored 2 points higher on some math benchmark.
Okay, tracking with you.
What happens when you try to integrate it and you hit a weird attention head bug? Or you need to run it on a specific piece of edge hardware and there are no pre-built quantization scripts for it.
Oh, you're basically stranded.
You are completely on your own. There are no Stack Overflow threads, no tooling adapters, literally no one in the ecosystem who has solved that problem yet.
You essentially become the sole maintainer for that integration.
Exactly. It's a nightmare. Contrast that with picking a model from the Ollama or Mistral families. The ecosystem around them is immense.
Because everyone is using them.
Right. If you encounter a bug, someone has already documented it on GitHub. Someone has already optimized the runtime for it.
Right. There are dozens of wrapper libraries built specifically for those architectures.
Exactly. You want the heavily trafficked, well-paved road, not the experimental prototype that's going to break your pipeline.
Okay, that makes a lot of sense. You optimize for maintainability and ecosystem tooling. So, okay, let's say we've picked our model. We'll go with a 7 billion parameter Mistral.
Solid choice.
We pull the weights. Now we hit the physical bottleneck, which is the runtime engine. Based on the deep dive notes, we have our standard native transformers library in Python. We have Ollama, and we have llama.cpp utilizing GGUF files.
Yeah, and this runtime decision is where you make or break your infrastructure budget.
So let's break down the mechanics here. It kind of feels like picking vehicles for different terrains, right? Like starting with the native transformers library, that's basically the high-speed F1 racetrack vehicle.
I like that, yeah, because if you are running native inference, you're essentially loading uncompressed 16-bit float weights directly into memory.
So it's huge.
Massive. It is built for maximum throughput, multi-node setups, and just pure native speed. But it demands massive, continuous blocks of high bandwidth memory.
Meaning you need expensive GPUs.
It demands enterprise-grade hardware. We all know memory bandwidth is the ultimate bottleneck right now. You cannot shove a 30 gigabyte uncompressed model into a consumer server setup and expect it to handle concurrent requests.
The system would just choke.
Instantly, which is exactly where the industry had to pivot hard into CPU-friendly inference. And that leads us to the reliable commuter vehicle, your analogy, llama.cpp, and the GGUF format.
Let's really dig into GGUF, because I feel like this gets glossed over way too often. It stands for GPT-generated unified format, right?
Right. And it replaced the older GGML format.
Because GGML was just too rigid.
Yeah, you couldn't easily add metadata to the model files without breaking backward compatibility. It's super fragile. GGUF fixes that by packaging the entire model, the weights, the architecture definition, all the metadata into a single file.
But just repackaging it doesn't solve the fact that it's physically massive, right?
Well, no. But the brilliant mechanism behind GGUF is memory mapping, or MAP.
Right, I've seen that term thrown around. How does MAP actually work under the hood here?
So instead of loading the entire massive file into your system RAM all at once, which, like we said, would crash most standard machines, the operating system maps the file on the physical disk to a range of virtual memory addresses.
Okay, so it tricks the system into thinking it's in RAM.
Kind of.
Yeah.
The CPU only streams in the specific chunks of the model it needs for the current calculation, directly from the disk to RAM exactly when it needs it.
Oh, wow. That's incredibly efficient. But memory dapping alone still doesn't solve the total size issue, right? Which is where quantization comes in.
Exactly. Quantization is the secret sauce here.
And I want to make sure we explain the reality of quantization clearly, because it's not just like a generic zip file compression algorithm.
Oh, far from it. Imagine taking a highly granular 16-bit color map, right? Like a beautiful photograph, and you force it into a 4-bit color palette.
You're going to lose all the subtle gradients. It gets blocky.
Right, you inherently lose the subtleties.
Yeah.
In the context of a neural network, you're taking these high-precision weights, which represent the micro nuances in the model's logic, and you are rounding them down to 4-bit or 8-bit integers.
So you are mathematically lobotomizing the model.
It's a brutal way to put it, but yes.
So how does it still function at all if you're crushing the logic?
Because of how the activations are distributed, researchers realized pretty early on that most of the weights in a trained network just sit clustered around 0. They don't do much.
Oh, interesting. So a lot of it is dead weight.
Essentially.
Yeah.
The massive defining logic paths, the extreme outliers, are what really dictate the model's actual reasoning. So advanced quantization techniques preserve those crucial outlier shades perfectly, while aggressively crushing the redundant near-zero weights.
Okay, so you lose a tiny fraction of theoretical nuance, but you retain the stark defining logic.
Exactly. And suddenly, that 30-gigabyte model physically fits into 6 gigabytes of standard system RAM.
Which fundamentally changes the deployment economics for a dev team. You can run highly capable inference on standard compute instances without fighting AWS for an expensive GPU allocation.
It democratizes the whole thing.
And then, of course, completing our vehicle analogy, you have Ollama, which is the push-to-start joyride for local tinkering, right?
Yeah, Ollama is fantastic. It basically takes that llama.cpp backend and wraps it in a beautifully simple Docker-like execution environment.
You literally just type Ollama run Mistral in your terminal.
And boom, it pulls the weights, quantizes them if needed, and spins up a local API endpoint automatically. It is the ultimate local development tool. You don't have to write any custom inference scripts.
Okay, but honestly, let me play the skeptic here for a second.
Bring it on.
Writing custom local inference endpoints, configuring GGUF files, managing quantization levels. I mean, this feels like a massive step backward into like pure infrastructure management.
It definitely takes work.
Right. So why wouldn't a development team just route everything to an OpenAI or Anthropic API endpoint, let them handle all this hardware scaling, and just focus entirely on the application logic?
Because it always comes down to unit economics and architectural strategy. It's the classic build versus buy debate, but amplified by a factor of 10.
Okay, explain that.
Relying entirely on premium cloud APIs is an incredible way to prototype. I recommend it. But it is a terrible way to scale certain types of operations in production.
Walk me through a scenario where that cloud-only approach breaks down.
Let's say you're building an application that processes thousands of background tasks an hour.
Like logging.
Yeah, maybe you're continuously analyzing server logs to flag anomalies, or running basic sentiment classification on every single incoming customer support chat, or even just parsing messy user text into structured JSON.
Okay, those are pretty simple tasks.
Right? Trivial high-volume tasks. If you send every single one of those requests to a massive multi-trillion parameter model via a paid API, you are literally using a supercomputer to do basic arithmetic.
Ah, I see.
The network latency adds up, but more importantly, the token costs will absolutely destroy your profit margins at scale.
So this is where the hybrid architecture we found in the notes comes into play. We don't just pick open source or our cloud, we implement a routing layer.
Exactly. A sophisticated hybrid architecture acts like a traffic controller.
How does it decide where to send things?
You deploy a highly optimized, quantized open source model locally on your own cheap servers or even directly on the client's device. That local model handles all the simple high-frequency tasks.
Because the marginal cost of processing those requests is basically zero once the server is running.
Precisely. And then you only route the highly complex edge cases, like the deep reasoning queries, or tasks requiring massive context windows out to the expensive cloud APIs.
You get the absolute best of both worlds. Fast and cheap for the easy stuff, incredibly smart for the hard stuff.
Exactly. It's the only way to scale profitably.
Okay, from an engineering standpoint, routing cheap, high-volume queries to a local instance makes total sense. But from a legal standpoint, this is usually where teams step on a massive landmine.
Oh, the licensing landmine, yes.
Right, because if we pull a model off Hugging Face to save on API costs and integrate it into our commercial backend, we have to deal with the fine print. And I feel like developers notoriously ignore licensing until they receive a cease and desist.
It is the absolute easiest way to accidentally sink a startup right now.
Oh.
Open source is a highly, highly loaded term in the AI space.
Because it's not always actually open source.
Right. Just because a repository is public on Hugging Face does not mean the weights carry an open source initiative-approved license.
Let's draw the lines for the listeners. The gold standards here for commercial use are Apache 2.0 and MIT, correct?
Yes, if you're looking at a model like many in the Mistral or Quinn families, for example,
Yeah.
and you see an Apache 2.0 or MIT license attached to the actual weights, you're in the clear.
Those are fully permissive.
Fully. You can modify the architecture, you can distribute it, commercialize the outputs, embed it deeply into proprietary software. You don't have to look over your shoulder.
But then we have the Meta models,
Oh.
the Llama family, which are incredibly popular. Meta heavily promotes Llama as open source, but it runs on a custom community license, right? And the details there are super specific.
Yeah, the Meta license is a brilliant piece of corporate strategy, but you really have to understand the boundaries. It's highly permissive for almost everyone, but it contains a very deliberate trapdoor.
The user limit trapdoor?
Right. It essentially grants you a commercial license for free unless your application reaches over 700 million monthly active users.
Which is the famous don't compete directly with Meta clause.
Exactly. If you somehow hit that user threshold, your license is automatically revoked, and you have to negotiate a custom paid agreement with Meta directly.
Now, realistically, for 99.9% of engineering teams tuning in, having 700 million active users is a total dream problem.
Right, you'll be popping champagne if you hit that problem. It won't affect a standard B2B SaaS startup.
But there are other stipulations in that Meta license that actually do impact everyday developers right from day one, right? Specifically around training.
Yes, that is the critical one. The license explicitly forbids using the outputs of a llama model to train or fine-tune a competing large language model.
So I can't use Llama to generate a bunch of synthetic data for my own project.
Well, you can't use it to generate millions of rows of high-quality data to train your own proprietary foundation model from scratch. They're actively protecting their moat.
Makes sense from their perspective.
So the ultimate takeaway here is, before you embed a model into the core logic of a commercial product, you must verify the license of the weights themselves, not just the inference code wrapping them.
It's a fundamental due diligence step. Okay, so we've mapped out the Hugging Face Hub, we have our selection framework, we understand the technical reality of quantization and map, and we've locked down the hybrid strategy and the legal boundaries.
We've covered a lot.
We really have, which actually perfectly leads us into a massive paradigm shift happening right now. Based on the notes, for the last few years, the entire industry assumed that intelligence scaled linearly with parameter count.
Right, the bigger is inherently better era.
Exactly. The underlying assumption was always that to get deep reasoning, you needed hundreds of billions of parameters, you needed massive GPU clusters to train it, and premium APIs to interact with it.
But that is completely changing.
Right. The latest generation of small language models, or SLMs, is just destroying that assumption. We're talking about models like Microsoft's Phi, Google's Gemma, and Alibaba's Quinn 2.5.
They are unbelievable.
We're seeing models with only 3 to 8 billion parameters stepping into the ring and completely outmaneuvering legacy models that are 10 times their size. How is that physically possible given the massive reduction in the neural network's capacity?
It all comes down to a radical shift in data curation.
The training data.
Exactly. The first generation of large language models were essentially just massive vacuum cleaners. They scraped the raw, unfiltered internet. Reddit threads, messy forums, disorganized code bases, just everything.
Just shoveling data in.
Right. And they needed hundreds of billions of parameters just to memorize and filter out all the noise and contradictions in that low-quality data.
So they basically used sheer scale to brute force their way to intelligence.
Exactly. But what researchers, specifically at Microsoft with the Phi project, what they proved is that data quality is significantly more important than parameter count.
So what did they change?
They stopped scraping the raw web. Instead, they started generating highly curated, synthetic, textbook quality data.
Let's dig into that mechanism. What does synthetic textbook data actually look like in the training pipeline? Like, who is writing these textbooks?
Other, much larger AI models, actually. Instead of hoping a small model learns logic by reading a messy forum debate where people are yelling at each other, researchers use highly capable models like GPT-4 to generate millions of perfectly structured logic puzzles.
Oh, wow. So perfectly clean examples.
Right. Clean coding tutorials, step-by-step reasoning traces. They curate a data set that contains almost zero garbage.
That's brilliant.
And when you train a small, lightweight architecture exclusively on this hyper-dense, logically sound information, The model doesn't need to waste billions of parameters memorizing the noise.
Because there is no noise.
Exactly. It learns the underlying patterns of logic and reasoning incredibly efficiently.
I love this. It's basically the difference between trying to learn physics by listening to 1,000 people argue at a noisy bar versus sitting in a quiet room with a perfectly written textbook.
That is the perfect analogy.
You can learn it so much faster, and your brain doesn't have to work nearly as hard to filter out the nonsense.
That is precisely how these SLMs punch so far above their weight class. They are highly focused reasoning engines rather than sprawling encyclopedias of internet trivia.
And the practical implication for software engineering here is just profound. Because an 8 billion parameter model, especially when it's quantized using the GGUF methods we talked about, runs effortlessly and natively on a standard laptop processor.
Without breaking a sweat.
It doesn't require a data center. It doesn't require an API key.
Which completely unlocks local-first AI development. I mean, we discussed the hybrid architecture earlier, right? Routing queries to save money.
Right.
But running a highly capable SLM locally isn't just about cost savings. It's about fundamentally shifting what an application can physically do. Think about the privacy implications alone.
Oh, huge.
If you are developing a healthcare application, processing patient records, or a local tool indexing a user's private financial data, sending that context out to a third-party API is a massive liability.
Sometimes it's straight up legally impossible due to compliance constraints. IONPA, GDPR.
Exactly. But with a local SLM, the data never leaves the physical silicon of the user's device.
Total privacy guarantee.
Total privacy. And beyond that, think about the user experience. You have zero network latency. You aren't waiting on a server round trip or dealing with rate limits. The inference happens exactly at the speed of the local processor.
And it works completely offline, too.
Yes. In secure, air-gapped environments, without any external dependencies, it changes the entire development loop.
Because when the intelligence is local, you can iterate constantly. You aren't paying a fraction of a cent every single time you hit compile and run a test prompt.
It completely removes the financial friction from the experimental phase. It is incredibly empowering for developers. The barrier to entry for building deeply intelligent, context-aware software has literally never been this low.
The ecosystem is unified, the runtimes are optimized for consumer hardware, and the models are shrinking while their actual reasoning capabilities are accelerating. It's an amazing time to be building. Well, we've covered a massive amount of ground today. From the absolute necessity of the Hugging Face API layer, navigating the nuances of quantization and map with GGUF files, routing traffic in a hybrid architecture to save our margins.
And obviously, the incredible potential of SLMs running strictly on local hardware.
Yeah. But as you step back and look at this entire landscape we've mapped out today, there is a lingering thought I really want to leave you with.
Oh, here we go.
If we are already at a point where a tiny, heavily optimized model can run natively on a laptop and outperform massive cloud models from just 2 years ago, where does this vector point?
It's a crazy trajectory.
Are we approaching a future where every single piece of software you compile, every background daemon, every simple CLI tool, every standard desktop app doesn't just ping a remote server, but actually ships with its own dedicated, specialized AI brain embedded right into the binary?
Just baked right in.
Right. A world where your code doesn't just execute static logic, but locally reasons about the environment it's running in. That is the paradigm we are actively building toward right now. Keep coding, keep optimizing, and we will catch you on the next deep dive.